Good morning, everyone. Thanks for joining us. We are, what time is it? A couple minutes to 11 Eastern time. We're going to give folks another couple of minutes to pile into the webinar, and we'll be starting 1 or 2 minutes after 11 o'clock. Thanks for your patience. Just sit tight for now. Thanks again for joining, everybody. We're going to wait another minute or so, and then we'll get started. Okay, Frankie, let's get started. Okay, welcome everyone. Thanks for joining us once again. It's been 3 or 4 weeks since we were last together for our webinar series called Rose. Frank, next slide, please. We got a great presentation for you today. I think many of you know Frank Da Silva from our West region. Frank's been in the business for over 30 years. How long have you been with us, Frank?
It's been 31 years now.
Oh my gosh. So we're really excited to have him. My name is David Chesnick. I'm the Global Marketing Director. And of course, everyone knows Peter Myers and Caitlin Clark from our technology group. The rules of the road today are the same as they've been for the last couple of months. Just make sure to mute your microphones if you haven't already. And I think they're all in silent mode to start anyway. We're not going to use the hand raising feature. As you know, we're going to be using the Q&A feature down at the bottom, and we're going to kind of curate all your questions as we go. And at the end of the presentation, when we get to the Q&A section, Caitlin will run through some of those questions and make sure that Frank and Peter answer them for you. The presentation is going to be available at the end of the presentation is going to be available to everybody in PDF form and also in video form afterwards. And you can reach out to us at webinars@resintech.com or your rep to get it. We'll also be sending out some links, and it'll probably appear on our YouTube channel as well. And then we're going to be collecting your feedback at the end of the survey as well via these QR codes. So if you've got your mobile phone handy, keep it handy. At the end, we'll show this QR code again for several slides, and it'll give you an opportunity to tell us how we're doing and what we can do better. So next slide, Frank. Without any further ado, I'm going to turn it over to Frank De Silva to talk about water softening. Go ahead, Frank.
Thank you, David, and thanks everyone for joining us this morning. It's nice to see everyone virtually, and I look forward to seeing everyone in person at upcoming conferences as we return to normal. There is light at the end of the tunnel. So today we're talking about water softening with ion exchange, the most common application of ion exchange in the world. These are the subjects we'll be talking about. I'm going to review terms briefly, talk about how softeners work. We'll go through a basic system design, and we'll also talk about, God forbid, what can go wrong. First, water softener terms. When I was in 4th grade, we studied the metric system because we were told everything was going to be converted to the metric system. Of course, that never happened. And here we are. We're measuring resin in cubic feet, water in gallons, capacity in kilograms per cubic feet, hardness in grains per gallon, regenerance as pounds per cubic foot. But leave the driving to us. We'll explain this all to you and keep these softener calculations understandable and easy to do. First, the most basic definition. Cations are positively charged, anions are negatively charged. Ion exchange is all about dissolved ions in water, and those dissolved ions have charges. Whenever I talk about any concept in ion exchange, I like to start out with the basic water analysis. Most all naturally occurring water sources contain these cations, calcium, magnesium, and sodium. They also contain sulfate, chloride, and alkalinity on the anion side. Other not so common cations can include potassium, iron, manganese, possibly even copper and zinc. But of course, for softening, we're concerned with calcium, magnesium. Here's some terms and units of measure that you'll see in the presentation, and of course, in your work with softeners. Parts per million or milligrams per liter is an interchangeable term. When we convert the parts per million to calcium carbonate equivalents, we divide by 17.1, and that gives us our grains per gallon loading. Grains is a rather archaic term. It actually has its foundings in grains of wheat. There's 7,000 grains in a pound. How about that? So how softeners work? Ion exchange resins are little plastic beads that take ions out of water and put other ions back in. So we're removing objectionable ions and replacing them with ions that we hope are, if not preferable, at least tolerable. In the case of softening, we're removing calcium and magnesium and replacing it with sodium. The sodium salts that are formed are highly soluble. Scaling is minimized. Also, the absence of hardness ions makes water easier to react with soap. It's easier to make suds and to clean. How a softener works. Most softeners are operated in downflow operation in a pressure vessel that has a packed bed of ion exchange resins with freeboard above them. Now, some important concepts here. The hard water enters the vessel, gets distributed across the resin bed. As the ions proceed through the bed, the calcium, the magnesium ions are exchanged with the sodium ions. The sodium ions, as I said, are very soluble. The TDS here is unchanged. The cation profile of the raw water is calcium, magnesium, and sodium. The softened water is all sodium. So we've changed the cation profile of the water. We have not changed the anion chemistry at all. The sulfate, the alkalinity, and the chloride levels are the same coming out of the softener as they are going in. Why water softening is so efficient? Well, at relatively low TDS and normal TDS levels that we see in drinking water supplies, the selectivity for hardness is very high. The resin likes calcium and magnesium a lot more than it likes sodium. And this is primarily due to valence. If we look at it simply, the calcium and the magnesium each have a valence of two positive charges, where sodium only has one. Low hardness leakage from the resin is achievable with softeners. And it can be quite chemically efficient, meaning that the amount of salt we use to remove X amount of grains of hardness is minimized. Here's a chart that shows what this preference actually is numerically. So, for example, a water with a TDS of 100, an 8% cation resin has a preference for hardness of 2,500 times more than sodium. Now, as we increase the TDS, we bump it up to 1,000, or we see a water with 100,000. You can see the ion exchange reaction. The standard softening ion exchange reaction is a lot less effective because that selectivity or that preference goes down. What does a softening resin look like? It's about 0.5 millimeter in diameter. It's a perfect round sphere. And this is an 8% cross-linked cation resin example that I'm talking about, the most common, of course. The weight is about 50 pounds a cubic foot. The density is 1.28. It sinks in water. It sinks in concentrated brine. Maximum temperature that it should be exposed to is about 250 degrees Fahrenheit. The total capacity as measured in a laboratory for an 8% cross-linked resin is 44,000 grains per cubic foot. And we're going to be talking about these capacities later on. So don't let that number throw you off, because I'm sure it's not one that you're familiar with if you deal with operating capacities. Important concept. The laboratory, we're measuring the complete total capacity of that ion exchange material. Operating capacity is the capacity of the resin when it's in use. I mentioned we're talking about an 8% cross-linked resin here. The cross-linking is made of divinyl benzene, commonly referred to as DVB. It gives the resin bead its strength. This is a strongly acidic cation resin. It's also referred to as a sulfonic benzene sulfonate or sulfonated styrene divinyl benzene copolymer. The ionic form that we use this resin in nearly all cases for softening, is the sodium form. What types of strong acid cation resins are there available for softening? The standard cation is an 8% cross-linked industrial quality cation resin. There's also 10% cross-linked. Of course, that's more divinyl benzene, so it makes the beads stronger, more resistant to oxidation. These 8% or 10% cation resins are available in either black or amber color. Aside from the color, these resins are identical in terms of physical, chemical, and operating properties. The only difference is the color. So it's your preference. Macroporous cation can be used in some extreme conditions. A macroporous cation has a cross-linking of greater than 12% up to 15 or 16%. And the way the macroporous cation resin is manufactured leaves it with discrete pores in the bead. It's like a Swiss cheese. So although it's stronger, because you have holes in the bead, there's less plastic, consequently lower capacity, about 15% lower. There's some specialty cation resins that are also used in the softening process. Fine mesh. A fine mesh resin is about 30 to 60 mesh in size. Standard cation resin, I should mention, is 16 to 50. 16 to 50, 0.3 to 1.2 millimeters. 30 to 60 mesh is the size of the fine mesh. It's got a greater surface area, a shorter ionic path. Most of the exchange sites in an ion exchange resin are inside the bead, greater than 95%. It's not a surface phenomenon. The ions have to get in and they have to get out for the process to work. So of course, a smaller bead has a shorter kinetic path for the ions, and you have that advantage using a fine mesh. Fine mesh is used in some of the high capacity brine efficient units. It's also useful in iron containing waters. However, it has a higher pressure drop because it's a finer medium. So it has its limitations there. Coarse mesh, 16 to 30 mesh, bigger beads, bigger space between the beads. That space is called the interstitial bed volume. Used in higher flow rates, it's a little less efficient in terms of the brine conversion and rinsing and that sort of thing because the beads are bigger, the kinetic path is longer. But this is primarily used when you need to accommodate a higher flow rate. And also we find uniform particle size in some softening applications. Packed beds often use it, and extra deep beds sometimes use uniform particle size resins. Capacity and leakage rules of thumbs. Now, a few slides earlier, I mentioned a total capacity of 44,000 grains per cubic foot, or divide that by 1,000, it's 44 kilograms per cubic foot. Let's talk about operating capacity now. Here's a range of different dosages of salt, of brine on the resin: 6 pounds per cubic foot, 10 pounds per cubic foot, and 15 pounds per cubic foot. And we have different capacity ranges at each one of those dosages. The most common rule of thumb for softener capacity is at 15 pounds per cubic foot of brine dosage, you can expect 30 kilograms or 30,000 grains per cubic foot. Now, the ranges that we give here are explained in the notes. The lower TDS gives a higher capacity and lower leakage. The higher TDS, and we're talking about background TDS, the higher TDS gives lower capacities and higher hardness leakage during the run. Let's look at those average leakage numbers. At the low dosage, you can see that's a pretty high leakage, 5 to 15 parts per million, depending on the condition of the water. Higher dosage, of course, will get you down to a lower leakage of 1 to 3. What happens when you need lower than that? There's many boiler feed operations that need 0.1 part per million hardness leakage. Well, in those cases, we go to countercurrent regeneration or perhaps a lead lag unit. We'll get into that a little bit more. Here's a graph that shows what those different dosages mean. The 6 pound dose, of course, gives the shortest throughput and the highest leakage. Here's our 10 pound in the middle and 15 at the end. And based on a 500 part per million TDS water, where 80% of that TDS is hardness, we get a throughput, look at this, we get a throughput of almost 1,200 gallons per cubic foot at a dosage of 15 pounds per cubic foot. Consequently, at the lower dosage of 6 pounds, we're only out to about 800 gallons per cubic foot between regenerations. A note here about efficiency. At the lower dosage, we're more brine efficient. At the higher dosage, we're less brine efficient. That is the amount of brine you use to remove the hardness. Here's another graph showing the hardness leakage versus the TDS versus the salt dose. And here's our dose on the x-axis from low to high. And you can really see the effect on this graph of the high TDS waters. Look at the 1,000 TDS. It's hard to get leakage down below 5 parts per million unless you go to some pretty heavy dosaging. And that's not real efficient in terms of brine consumption. So higher TDS means you have a lower preference, and it's hard to overcome that lower preference. And that results in increased leakage during service. More salt, reduced leakage. One big takeaway about today's presentation: the more salt you put on that resin, the lower the leakage, the higher capacity. One more graph. This is showing the difference between co-current and countercurrent operation. So co-current means that we're introducing the brine in the same direction as the flow. I have some drawings that will show that later on in the presentation. Countercurrent, we introduce the brine opposite to the service flow. And in almost all cases, the service flow is downwards through the vessel, and the brine flow for co-current is in the same direction from the top to the bottom. Countercurrent would be from the bottom to the top. So what do we get? What benefits do we get from countercurrent? Look at this. We have cut the average hardness leakage in half, down to 0.68 part per million from 1.2, which is the hardness leakage we were getting at a dosage of 10. I'm going to go through a simple softener design here, and it's an example that you can use for either designing new softeners or perhaps reviewing a design of a softener that's been in service for a period of time. First, let's talk about the applications that softeners find themselves in. The definition of the application, or defining the system, is often defined by the application. Let's talk about the most common by far is residential. In terms of numbers, there's hundreds of thousands of softeners that are used by households for residential use. And these systems usually have a pipe size of 3/4 inch or less. They're characterized by high peak flows compared to average flow. You know, think about the water that you use in your home. There's high peak flow in the morning and in the evening with showers and washing machines and dishwashers. Intermittent usage is another characteristic. Most of these tanks are made out of fiberglass. The resin bed depth is limited by whatever size tank can fit. Salt efficiency is becoming increasingly important for residential units because most of these units have brine that are discharged to municipal sewer, and municipal sewers municipal utilities, of course, want us to minimize the sodium or chloride discharge. Color, taste, and odor are also very important for residential units, as well as ANSI NSF 61 certification. Commercial systems are a step up in size. They're typically about 25 to 50 GPM, maybe even up to 100. They use larger tanks, and they can be found in institutional settings, restaurants, hotels, laundries, car washes. Throughput capacity is important. Modest hardness leakage is acceptable. And what do all of these applications have in common? Look at this. They all use soaps. So soft water gives them a huge savings in soap consumption. Lastly, and the largest applications are the industrial municipal applications that we see. Larger vessels, these are mostly custom built vessels, steel construction, ASME code tanks. Where do we find these? We find these in large factories, boiler water treatment, power plants. These are characterized by high flow rates, continuous operations. It's a critical operation, low hardness leakage requirements. And how do you know a facility has this type of larger softener in it? If they're producing steam, if you're driving through an industrial area and there's steam venting from the roof of that factory, you can bet that that steam is venting from a boiler or other heat process. And if they're making steam, they're at a minimum softening the water. What are the practical limits for sizing? If you look at the published literature for ion exchange resins, you'll see some pretty wide ranges that are given. You know, service flow, 1 to 10 gallons per minute per cubic foot. That's pretty wide. So we've narrowed it down here in this chart down to 2 to 4 gallons per minute per cubic foot preferred. This is what's called the kinetic flow rate. This is the contact time. It can be converted to empty bed contact time if you're familiar with that from using carbon. Another flow guidance number that we use is the gallons per minute per square foot, or the linear flow rate. And this is the flow through the cross-section area of the vessel. 2 to 20 is the wide range. We like to see it around 8 to 12 gallons per minute per square foot. What are the bed limitations? Bed depth limitations. Minimum 2-foot bed depth, maximum 8. Probably better off in the range of 4 to 6. The deeper the bed, the better you'll do in terms of ion exchange. Taller, skinnier ion exchange beds are almost always better than shorter, squat ones. Pressure loss across the bed, it can handle 25 pounds per square inch or more, but it's best to keep it below 10 when you're designing a system. Inlet contaminants. Here's an important concept. Ion exchange resin is a plastic, styrene divinyl benzene. So it does oxidize when in contact with strong oxidants, such as chlorine. 0.3 part per million of free chlorine is considered an acceptable level. The preferred level on the inlet is 0. Turbidity. Ion exchange resins, unfortunately, are also a good physical filter. Let's keep suspended solids out of the bed. Turbidity of 1 or less. 0, of course, would be best. Iron. Iron's a subject of a separate discussion. It's a rather complicated issue with softeners. Softeners will remove iron both by ion exchange, and if the iron is in the ferric form, the undissolved form, it will also filter it out. Iron can be a problem in ion exchange beds. It can be remedied by the use of resin cleaners. More on that later. But in general, if you can keep the iron below a part per million coming into the bed, the better. Process design. Here's the example that I told you we'd be going through. So there's a couple of ways to approach this. You calculate the hardness load. What are the grains per gallon of hardness that's in the influent water? Determine the capacity and the leakage, and then set one variable, calculate the other. Choose a resin volume, calculate the throughput, or pick a throughput that you need, X amount of gallons per day, and then calculate the resin volume you'll need to satisfy that requirement. And then once you've sketched out those parameters, you can check it against these guidelines and see if it all fits. So here's our sizing example. This situation has 100 gallons per minute of average flow. The hardness in the influent water is 10 grains per gallon. We want 2 full-size softeners, that is 2 100% capacity softeners. So we'll have 1 softener on line, 1 softener on regeneration or standby. 25 cubic feet of resin is selected, and from the published specifications or a performance projection provided by the resin supplier, we've determined that the capacity of the resin, 8% cross-linked resin on this particular water is 22 kilograms per cubic foot at a 6 pounds per cubic foot salt dose, or of course, 22,000 grains per cubic foot. And I should mention here that we regularly perform these performance projections given the water analysis. And for softening, it's rather straightforward. We don't need a lot of an extensive list of water parameters to do this. Send us the TDS, calcium, magnesium, sodium, and we'll supply that for you, give you the capacity range over various brine dosages. Continuing with our sizing example. So what is our throughput capacity going to be per vessel? We know we have 25 cubic feet of resin in each vessel. We know our capacity is 22 kilograms per cubic foot, and we know we have 10 grains per gallon of hardness in the feed. By that calculation, we find that the vessel is capable of 55,000 gallons of softened water between regenerations. How long is that going to last? Our flow rate is at 100 gallons per minute. That converts to 550 minutes or 9 hours. So you'll be regenerating basically once a day. And this is an acceptable throughput for most factory type settings where the work hours may only be 8 hours a day. Let's check that vessel size, or let's firm up the vessel size. We know we want 25 cubic feet in the vessel, and we want at least a 4-foot bed. So divide that 25 cubic feet by 4 feet, and we get a dimensional number of 6.25 square feet. If we go to our chart that shows what the square footage surface area is in different diameter tanks, we see that a 36-inch diameter tank has 7.07 square feet of surface area. So we divide the 25 cubic feet by the 7.07, we see that our bed depth is 3.5 feet. Perfect. And adding in the freeboard requirements, we'll go with a 3672 tank, very common size tank. When we put the tank in service, and it does exhaust because the resin, of course, has a finite capacity, and in this case, it's going to exhaust in 9 hours, we need to regenerate. What are the steps of regeneration? Backwash, brine injection, slow rinse, and fast rinse. The backwash fluidizes the bed, classifies the resin beads, which helps to minimize differential pressure, hopefully gets rid of suspended solids, gets rid of broken beads, and prepares the bed for the introduction of the brine. The backwash usually takes about 10 to 20 minutes, perhaps less on an ultra clean water, more on a turbid water. Backwash water temperature affects the expansion of the bed. Very important concept here. When I give these seminars live, I always ask the audience, what gives a better backwash, hot water or cold water? Most people get this wrong because cold water gives you a better backwash. Why? Because cold water is denser. So cold water expands the bed more. Every November at Resin Tech, we get emergency orders for softening resin that's been backwashed out of the vessel because they were backwashing at too high of a flow rate. And when the water temperature changed by the seasonal variation, they blew resin out of the vessel to waste. So let's take a look at this. So for our example of the 36-inch diameter softener, we want 40% expansion, and our water temperature is about 60 degrees. And we see that we need 4.5 gallons per minute per square foot. 4.5 times 7 gives us 31.5 GPM backwash flow rate. Introduction of brine. We're using 8 to 10% brine here. Well, we're using 10% brine in our example, but you would want to use a minimum of 8%, which correlates to a 30% saturated, 30% of saturated brine. And that adheres to the 30-30 rule. You want 30% of your saturated brine for your dilute brine, and you want to contact the resin for about 30 minutes, a minimum of 30 minutes. You can't go wrong there. And in our example, we're using co-current regeneration. It's downflow the same direction as the service flow. Brining calculations, this is how we figured that out. 25 cubic feet times 6 pounds a cubic foot, 150 pounds. And we take that 150 pounds and divide it by how many pounds per gallon are in the saturated brine, how many pounds per gallon are in the 10% brine. And the difference between those two numbers is how much dilution water we'll need. How do we make the dilute brine? We suck saturated brine out of the brine tank. We get the dilution water from the city water, put that into an eductor. The dilution water is the motive force to suck up the saturated brine. And lo and behold, coming out of that eductor is the 10% dilute brine. This illustration shows the volumes, the time, and the ultimate flow rate for each one of those streams. What's next? So the slow rinse. At the end of the brine introduction, at the end of that 30 minutes, that vessel is full of the best brine that resin is going to see. Most of the work has been done in the, say, the first 15, 20 minutes of the brine introduction. So instead of rinsing out this brine from the tank quickly, we want to bring it through and down through the bed at the same flow rate that the brine was brought in, the dilute brine was brought in. And this is the slow rinse or the displacement step. This usually takes about 30 minutes. Lastly is the fast rinse. This brings us back to quality, gets rid of any traces of salt and hardness, and the unit is back ready to go in service. Here is our completed worksheet of what I just went through: the backwash, the brine ejection, the slow rinse, and the fast rinse. Total time, 90 minutes. Total volume of wastewater, 1,000 588. Here's a cut diagram of a typical household softener. The typical household softener has one connection at the top that the head is threaded into. It's got a riser tube that goes down to the bottom, so the water comes in over and through the bed, gets collected by the bottom distributor, up the riser tube, and out to service. For larger installations, however, especially that diameters that require a separate brine distributor, this is what the inside of the vessel will look like. Our inlet at the top, it goes through some type of distribution or baffle plate, goes through the bed and out through the effluent. We can sometimes use a separate brine distributor that sits on top of the bed, a few inches above the bed. So the brine is not diluted when it's initially introduced to the bed. It's a lot more effective. Softener troubleshooting. What can go wrong? What do we experience in softeners? And of course, if we were live, these are questions I would pose to the audience. What problems have you seen out there? I'm sure that if you've been around softeners for a period of time, you've seen high pressure drop. High pressure drop most commonly is caused by solids buildup. You know, if you're not backwashing those solids out, it will build up on the resin. And just like any other filter, that's going to increase the pressure drop. Also, resin oxidation makes the resin beads softer. It can deform under pressure. Deform those beads, they're not round, but they flatten out, they pancake. You're going to get a higher pressure drop. Short runs, you're seeing lower capacity than expected. You could have lost resin during backwash, or perhaps through degradation, the resin beads break and you backwash them out. Low resin capacity through oxidation or fouling. What if you have a combination of short runs and hardness leakage? That really points to an improper regeneration. So what do you need to do? One of the things that I do whenever I'm on site, I open up that brine tank and make sure that there is brine, that there is rock salt in that brine tank. You can also perform an elution study. And an elution study is where we measure the percent brine that's coming out of the vessel during the regeneration process, during the brine injection and the slow rinse step. Steps to troubleshooting. Review that regeneration procedure. Are the flows and times what they need to be? Recalculate the throughput and the leakage based on current conditions. What do I mean by current conditions? I can remember being in a 100-year-old textile mill in North Carolina some years ago, and the softener they had in there was decades old. Let's say it was 30 years old. Well, that softener was designed on a water analysis that was taken 31 years ago. You think the water analysis has changed over 31 years? Of course it has. So it's important to look at what the current conditions are. What is that softener that was designed for an older water analysis? How does it behave in the current water analysis? So when we make those comparisons, we calculate our results on the current conditions, compare it to the actual field results. Do they match? If they don't match, let's find out why. Always a good idea in the larger units to take a resin sample for analysis. The Resin Tech laboratory can perform those tests. I'll more on that in just a few minutes. Of course, you can always call us for advice. We're available for real-time troubleshooting. What do we need to know? And this does not only go for the troubleshooting aspect of a water softener, but for the design of a water softener. What is the TDS? What is the pH and temperature? And it's also good to know the mins and maxes for these parameters. What is the basic inorganic analysis? The calcium, magnesium, sodium, chloride, alkalinity, sulfate, and yet another shameless plug, Resin Tech does provide these water testing services through our laboratory services. Are there oxidants present? Is there chloramine or chlorine? Are there suspended solids? Another thing to remember here is that a water analysis that we obtain is a snapshot of what the water looks like on that particular day. For groundwater sources, you know, there's not a lot of seasonal variance. But for surface water or lake or a river, you will see seasonal variances. So it's good to build in some engineering factors when you're designing a new system. And it's also a good a good thing to keep in mind when we're troubleshooting. You know, this water analysis snapshot, is this really what the softener is seeing day in and day out, month after month? Monitoring the performance, this is typically done in the larger industrial commercial systems. Monitoring the feed water hardness, the effluent hardness. What is the differential pressure across the bed? What's the run length in gallons? How much salt is being used per regeneration? And how much rinse water is being used? Rinse water can be a good indicator if the resin is fouled. The fouled resin usually requires more rinse water. Some common mechanical issues that are worth mentioning, since we're talking about troubleshooting. Keep your approach simple. You know, just like troubleshooting a computer. Is it plugged in? Is there salt in the brine tank? Has the system experienced resin loss? Is there some type of impairment with the brine injection system? Is the control valve operating properly? And again, I influence. Don't overlook the simple solutions. A word about resin fouling. There's different types. There's physical, chemical, and biological fouling. Physical, of course, is the collection of suspended solids and problems with iron. Chemical fouling, iron also has its own form of chemical fouling. Organic foulants, oils, greases, polyelectrolytes that may have been used upstream. Biological fouling, what is growing in your resin bed? Is there mold or algae or bacteria? This can be a problem with intermittently used softeners or softeners that sit over time. Inlet water chlorine guidelines. I touched on this a little bit previously. Chlorine up to 0.3 part per million, not much of a problem, but as that chlorine increases, it is a problem, and it will oxidize and decross-link that resin, making it softer, breaking the beads eventually. And here's some photographic examples. Other factors can contribute to this oxidation and almost act like a catalyst in this oxidation reaction. The presence of iron or manganese, higher temperatures. And as we really break down the resin, you know, at the high chlorine levels, you might even form some trihalomethanes in the effluent of the unit. Is resin cleaning practical? For physical fouling, it's very practical. Chemical fouling, it's effective, but the chemicals you use to clean may mean that you have to do it outside of the vessel because of the materials of construction. Biological fouling, it is practical, but you need to be really careful because we're talking about applying yet another oxidant to the resin to kill the bugs. Resin Tech makes a softener treatment solution called ResStore. And in a residential scenario, for example, you can put a quart of this into your brine tank once a month, and it'll prevent iron fouling. It cleans the surface of the bead. It's a good preventive maintenance step to use. Resin sampling. Whenever possible, take a core sample of the vessel. And by that, I mean use a 1/2 inch or 3/4 inch piece of PVC pipe, put it into the bed from the top to the bottom, plug it off, draw it out, and now we have a sample from the top to the bottom of the bed. I always can tell when a maintenance guy has opened up an industrial softener and scooped some resin off of the top of it with his coffee mug, because we get a sample of resin in that's 100% cracked beads. But a core sample will tell us the real story. We expect the top of the bed to be the most oxidized beads because they're the lightest, and that's where they end up after backwash. When you take the sample, send it to us with as much information as you can regarding that sample. Is it, how old is it? What's the model number? Is it regenerated or exhausted? And we will provide you with a test result that include capacity, the moisture content, the whole bead count, a nice photograph of the resin beads. We can also do optional tests, including site analysis and what effect cleaning in the field has been, and a screen analysis. So let's review what we've talked about here, especially when it comes to our troubleshooting. Keep it simple in terms of design if you're designing something new. The commercial industrial softeners that require very low leakage or high throughput will may require some assistance from companies like Resin Tech. So don't hesitate to call us, send us the water chemistry and what the effluent requirements are. We can calculate the leakage and the leakage at different dosages and consider countercurrent regeneration. Remember that TDS influences both capacity and leakage, and those are the things that we can accommodate into our evaluation. So troubleshooting requires a little bit of detective work. What were the original design specifications? What was the original water analysis? What is the expected performance versus the current conditions? What is the run length and the leakage that you see today? Resin sample, always a good idea to take. And in terms of the larger industrial units, not a bad idea after a year or two of service to pull a resin sample every year. Let's track the progress, or I should say the degradation of that resin, so you can get an expected lifetime estimate. Lastly, ongoing maintenance. I mentioned the resin cleaner. That's always a good idea. Do you need to give the resin the softener a vigorous backwash quarterly or something like that if you have a buildup of suspended solids? We at the Resin Tech laboratory, we test thousands of resin samples per year. We get many softener resin samples in from the field, and by far the most common problem in the softening resins is that there's dirt in the resin. There's suspended solids that have built up in the resin. Oxidation is probably the most common problem. But with that, let's see if there's any questions.
Frankie, thank you very much. Before we head into the questions, I just want to remind everybody the QR code that you see on your screen. If you have your mobile phone with you, take a moment, scan it. You'll see it on the next slide as well. But we really want your feedback. It's important to us, and it's useful to help make these webinars better and better with each subsequent webinar. So Caitlin, if you're ready, you can guide us through some of the questions that we received.
Sure. So first question, I see standard max capacity numbers of 30,000 and 32,000 grains per cubic foot. Why do we get different max capacity numbers?
So the maximum capacity numbers, the difference in the maximum capacity numbers is a reflection really of the TDS of the water and the amount of the hardness that constitutes that TDS. Now, if the question is also regarding the relation of those numbers to the total capacity number of 44,000 that I represented earlier, in service, we never restore the resin bead to 100% in the sodium form.
Right.
It's an equilibrium relationship. We put so much, we dose the resin with X amount of pounds per cubic foot, and we get X amount of grains per cubic foot in return.
So why is co-current regeneration more efficient?
Well, it depends on how you define your efficiency. It's not necessarily more efficient. We'd have to look at that on a case-by-case basis. Co-current is simpler. Co-current uses a higher percent brine, a higher percent dilute brine, and a higher dosage. So your let's call it the water efficiency is better. The brine efficiency may be lower.
Right, and a lot of times you're trying to get that extra low leakage, so you might be underrunning the softener by some people's.
Correct.
definition.
And anytime you underrun the softener, that is, you're not using up all the capacity during the service run, you have wasted capacity, which translates to wasted salt, which translates to lower efficiencies.
Okay, what does classify the bed mean?
What does classify the bed mean? So when we talked about what the beads looked like, we have a size range of 16 to 50 mesh. It's an inverse relationship. The 16 are the larger beads, the 50 are the smaller beads, and they're distributed in a bell-shaped curve. So most of the beads are in the 20 to 40 mesh range. But when we backwash the bed, the larger beads settle to the bottom, the finer beads settle to the top, and you have the gradations throughout that bed. So for the most part, you have beads that are the same size next to each other. And when you have beads the same size next to each other, you actually minimize the pressure drop because you don't have little beads filling in the spaces between the big beads. So that's what we mean by classifying the bed. Always a good idea, especially upon startup, to give the softener a vigorous backwash. Classify that bed.
Okay. And is there a particular kind of resin that we would recommend when you need to soften and you also have manganese in the water that would also need to be reduced?
So, you know, I didn't get into this because this is clearly the subject of a separate seminar, the accommodation of iron and manganese, or even the removal of iron and manganese from a water supply. Iron and manganese behave the same in many groundwaters. If they're present, they will be present in a dissolved form, and they will be removed by ion exchange. However, if they come in contact with any oxygen, such as during the backwash step, they can be converted to the ferric or manganic form, which is undissolved, and they will precipitate in the bead or on the bead. This is where a resin cleaner comes in handy because it will redissolve that stuff off. The fine mesh beads, to answer the question, the fine mesh beads are what you would want to use in those instances where you have iron and manganese present in the water. The fine mesh gives a more vigorous backwash, and a lot of the iron and manganese fouling occurs on the surface of the bead. More vigorous backwash, you'll be able to bump that material off of the bead.
Okay. And max service flow rate, how does that relate to pressure loss?
So max service flow rate, the higher the flow rate, the higher the pressure drop is going to be. So there are constraints, of course. The reason that we have those limits is that if you exceed those limits, you will have, not only is there a risk of equipment failure, but you can cause improper distribution in the vessel.
Okay, how about, does backwashing increase the total dissolved solids?
Does backwashing increase the total dissolved solids? It does in the backwash wastewater, because hopefully those suspended solids are getting backwash out of the vessel during the backwash step. Backwashing should not increase the total dissolved solids or total solids, I should say. It will not increase the total dissolved solids coming out of the vessel. And a distinction here between total solids and total dissolved solids. The backwash is getting rid of the total suspended solids.
Right. Okay. I have a softener that's leaking magnesium, but not calcium. Is there an obvious reason for this?
Yes, it is. Yes, there is. So the resin likes sodium, but it likes magnesium better than sodium. It likes calcium better than magnesium. So when a softener begins to hit the end of its breakthrough curve, the end of the service run, guess what type of hardness is going to leak first? It's going to be magnesium. So if magnesium is appearing, that means you've got a shortened run. In fact, the hardness test out there that changes, it's a colorimetric test, it changes from blue to pink. That's a measure of magnesium. It's not measuring calcium, it's measuring magnesium, because we know the magnesium is what comes off first. The ion exchange resin in softening, as it is in deionization and other applications, is a chromatographic removal of ions. So at the top of the bed, at exhaustion, at the top of the bed will be mostly calcium. At the bottom of the bed will be mostly magnesium.
Great. And if a client wants to sanitize their resin bed, is that okay to do without harming the resin? And how would you go about doing so without harming the resin?
A good question. There's if you Google my name and resin sanitization, or Google Peter Meyer's name and resin sanitization, we've both published articles on this. And the most common sanitization chemical at your disposal would be chlorine. And you can use chlorine at a relatively high ppm for a short period of time to sanitize the resin and kill the bugs. But be very careful, follow the procedure. Do not exceed the contact time that's recommended.
If we do backwash into a protected area, what would be the impact on the environment?
If we do backwash into a protected area, what would be the impact on the environment? So by backwash, I'm assuming that you mean the entire regeneration process, because that's the term that dealers and some OEMs use for the regeneration process, is the backwash. So I'll assume that's what you mean. So you will have an elevated TDS in that wastewater, and we can actually calculate, what the levels of sodium chloride will be. It's always important to find a good disposal source for the waste brine in particular. The actual backwash step, the fast rinse step, if you segregate those are easy to dispose of, because you're not, there's no sodium chloride brine in those, or very, very little. And now when I think back, the one of the first answers that we had today about backwash increasing the TDS, I believe that may be a reference to the entire regeneration process. Yeah, so regeneration disposal is important. Check with your local authorities. There's some regions of the country that allow the brine disposal to take place in the municipal sewer. Other have limitations.
Okay. And then for precipitated iron, does it require higher backwashes to get it to backwash out? Thus, fine mesh resin typically is backwashing at a lower flow rate?
In a word, yes. I like simple questions like that. In a word, yes. You get a better backwash with that fine mesh resin. Not so much that the fine mesh resin requires a lower flow rate, but gives you a more vigorous flow rate. Those beads are easier to fluidize. And something that I'd like to add, I saw a comment in the chat section having to do with the manufacture of ion exchange resins. So Resin Tech is in the final stages of making our new resin factory. It's a copolymer plant, the first one built in the US in 30 years. We're going to make US made softening resin. The process that we're using for that softening resin is a solvent-free process. Most softening resins in use today use a solvent process, and it's always important to minimize the solvent before use. It can contribute to color, taste, and odor. But the new process that we will be using at our new factory is a solvent-free process. Thought I'd like everyone to know that.
Frank, what's the practical benefit of that to customers and softening, and then for other applications as well, where they might be incorporating cation resin?
Well, the immediate practical benefit, of course, is the minimization of color, taste, and odor in the residential world. As we go up into the industrial world, however, the appearance of any organics in the effluent of an ion exchange resin has a real impact in the ultimate water quality required by the customer. And I'm talking about TOC levels, or total organic carbon. The high purity mixed beds that we make at Resin Tech that deionize water provide theoretically pure water, 18.25 megohm resistivity, in terms of the presence of ions. Well, what about unionized stuff, the organics? Well, we measure the TOC. And by using a clean cation resin source, the TOC will be minimized.
Thanks, Frank. Why don't you hit the last slide for me? I think it's too advanced from where you are, and we'll just tell everybody what our next presentation is going to be on. So on May 26th, that's again a Wednesday at the same time, 11 Eastern, Bill Coble is going to be taking us through deionization fundamentals. Bill's been with the company for, I don't know, 11 years, Bill, 12 years, something like that. We're really looking forward to having him present on this subject. So I hope you all join us. We'll be sending out another email to that effect. And the more of you that register, the better. So thanks, Frank, for all your hard work, and Caitlin and Peter and everyone who joined us today. And we'll see you on May 26th. Don't forget to scan that QR code one last time. Make sure you give us our feedback on today's presentation. We'll see everybody in a month. Thanks so much for joining us. Bye-bye.